we want to evaluate the indefinite integral. So looking at the integrand, notice how we have the square root of 9 minus y to the fourth, which fits the form of the square root of a squared minus x squared. So we'll perform trig substitution to determine the antiderivative. Notice how in this case, a squared equals 9, so a equals 3. We don't have x squared here, we have y to the fourth. So instead of letting x equal a sine theta, we'll have to let y squared equal a sine theta. And therefore, we'll perform the substitution, y squared equals 3 sine theta. And now we'll find differential y. The derivative of y squared with respect to y would be 2y, so we have 2y dy equals, the derivative of 3 sine theta would be 3 cosine theta, so we have 3 cosine theta d theta. Let's go ahead and solve this for y dy by dividing both sides by 2. Now notice how we have y dy here, but we don't have y dy as part of our integral. So we'll deal with that in just a moment. But for right now, let's go ahead and model angle theta using this right triangle. So if y squared equals 3 sine theta, notice that if we solve this for sine theta, we'd have sine theta equals y squared divided by 3. So if this is our angle theta, we can label the opposite side y squared, the hypotenuse 3, and therefore this leg here would be equal to the square root of 3 squared minus y to the second squared, which would be 9 minus y to the fourth. Now again, to perform this substitution and write this integral in terms of theta, we need to have a factor of y dy. So to get this extra factor of y in the numerator, we'll go ahead and multiply our integrand by y over y. So this would be equal to the integral of y times the square root of 9 minus y to the fourth divided by y to the fourth dy. And now we'll perform our substitutions. We know from our notes that by performing this substitution for y squared, the square root should simplify to 3 cosine theta, but let's go ahead and show that. So if we look at just the square root, we'd have the square root of 9 minus y to the fourth, since we have y squared equals 3 sine theta, would be 3 sine theta squared, which gives us 9 minus 9 sine squared theta. If we factor out the 9, we would have 9 times the quantity 1 minus sine squared theta, which equals cosine squared theta. And notice how this does give us 3 cosine theta. So by performing the substitution, this square root simplifies to 3 cosine theta. Next, y dy is equal to 3 halves cosine theta d theta. But let's go ahead and factor out the 1/2. So we'll write this as 1/2, and then we'll have in the integrand 3 cosine theta, and of course d theta. So again, y dy equals 1/2 times 3 cosine theta d theta. And now for our denominator, we have y to the fourth. Well, if y squared equals 3 sine theta, then y to the fourth would be 9 sine squared theta. Now let's simplify and find our antiderivative on the next slide. Notice how here, these 3's simplify with the 9. So this gives us 1/2 times the integral of, we'd have cosine squared theta divided by sine squared theta. Now I know this simplifies to cotangent squared theta, but we don't have an integration formula for a cotangent squared theta. So let's write this in terms of sine by substituting 1 minus sine squared theta for the numerator. So this would give us 1/2 times the integral of 1 minus sine squared theta divided by sine squared theta. And now if we break this up into two separate fractions, we would have 1 divided by sine squared theta minus sine squared theta over sine squared theta. Notice how 1 over sine squared theta simplifies to cosecant squared theta, and there is an integration formula for cosecant squared theta. So we have 1/2 times the integral of, again, cosecant squared theta, and of course sine squared theta divided by sine squared theta equals 1, so we have -1. And now we can find the antiderivative with respect to theta. This would be 1/2 times the quantity. The antiderivative of cosecant squared theta with respect to theta would be negative cotangent theta. The antiderivative of 1 with respect to theta would just be theta, so we have minus theta, of course, plus c. Now remember, we want to find the antiderivative with respect to y, not theta. So now we'll perform a substitution for negative cotangent theta as well as theta. So if we go back to the previous slide, this is why this triangle is so helpful. Cotangent theta is equal to the ratio of the adjacent side to the opposite side, so it's equal to the square root of 9 minus y to the fourth divided by y squared. So here we have 1/2 times the quantity, we have negative square root 9 minus y to the fourth divided by y squared. Now for theta we have a couple options. We could use any of the inverse trigonometric functions to represent theta. Let's go ahead and use this equation here, sine theta equals y squared divided by 3. If sine theta is equal to y squared divided by 3, we can take the inverse sine or arc sine on both sides of the equation, and therefore theta would be equal to arc sine of y squared divided by 3. So we have minus arc sine of y squared divided by 3. And again, we didn't have to use arc sine, but because we already had this equation for sine theta, it seemed the most obvious. Of course, then we still have plus c. So if we wanted to, we could distribute the 1/2. That would give us negative the square root of 9 minus y to the fourth divided by 2y squared minus 1/2 arc sine of y squared divided by 3 plus c. So this integral did have some tricky substitutions that we had to be careful about. I hope you found this helpful.